before we get started? Okay. All right. So I'm gonna sort of rehash the linear transport example that we worked on last time. So if you remember, we were talking about the linear transport equation, and let me just get a little more specific. So this is a partial differential equation. It's first order. It's defined for x is, let's say, on the reals, or let me be a little more general and say this could be a subset omega of the reals. The main cases that we'll deal with are where this is on the infinite line, and then where it's on the half line, the positive values of x. So t here is taken to be greater than 0, and then on the initial value y equals 0, we have some function u0 of x that specifies this, okay? So if you recall, okay, when our domain is just equal to the reals, then the solution that we have is that u of xt is equal to u0 of x minus ct, okay? Now, if we move beyond that, if we move beyond that and we think about, just gonna mute everybody. You can unmute yourself whenever you like if you have a question, or you can put it in the chat. Okay, so if we then look at the case where we have that the domain that this is defined on is just the positive reals, or x is greater than or equal to 0, we have to introduce a boundary condition. And this is what we did last time. So in this case, we have an initial boundary value problem, okay? It just means we have a boundary condition and we have an initial condition, okay? And so in this case, u of x0 we'll say is equal to some function phi of x, and u0 of t is going to be equal to some function psi of t, okay? And these are each respectively defined on x is greater than or equal to 0, or t is greater than or equal to 0, okay? Now the issue here that we addressed last time is that we now don't have just a single line that determines the solution thereafter to our initial boundary value problem. We have this line along x and this line along t, okay? Along which our initial and boundary values are defined, okay? But the important thing here is that solutions, okay, u are equal to some unknown function x minus ct, okay? So, and this function is constant, okay, along what are called the characteristics, which are all of the lines that are specified by x minus ct equals some constant value psi, that little squiggly there, okay? And the most important one of these for this problem is this one here, the line x equals ct, because that divides solutions into the region that's determined by phi of x and the region that's determined by psi of x, okay? So what's going to happen is that all of the points that live on this side, I'm sort of drawing all the characteristics that emanate out of psi of t, are going to be determined by this boundary condition here, okay? All the transport equation does is it takes that boundary condition and propagates it up and to the right, okay? Over here, all the transport equation does is that it propagates this boundary, this initial condition, again, up and to the right. That's what those lines are that I'm drawing there, okay? And so what we did last time is we sort of split the problem in half. We said, I'm going to solve for what the function looks like to the right of this representative characteristic, this sort of dividing line, and what it looks like above it, okay? And what we found is that if we do that, and we write u of xt equals f of x minus ct, okay? Then we have that the right-hand side is given by looking at the initial condition, u of x0, which is going to be where u is just equal to our unknown function f, okay? So remember, at this point, f is still an unknown function. We're going to use the initial condition to specify it, okay? So in this case, f of x is equal to, well, if I just look back at our initial condition here, it's equal to phi of x. That's a function that I know and that I'm given. You know, it could be any function, but that's my initial condition. So f of x is equal to phi of x as long as x is greater than or equal to 0. And then to get the other part of my solution, I use my boundary condition that says that u of 0t is equal to f of minus ct. I just plugged in x into my equals 0 into my unknown function. And I say that that has to equal my boundary condition, psi of t, okay? Well, in order to get everything sort of working right, I need to change variables. So I write y of equals minus ct. And I can change variables and get t equals minus y over c, okay? And this all put together tells me that f of y is equal to psi of minus y over c whenever y is less than or equal to 0, okay? So this is like the other half of my solution. It's the part that, sorry, I'll flip back here, that lives above this dividing line characteristic here, okay? And now I have my full solution, which is u of xt is equal to, it's going to be equal to phi of x minus ct whenever x is greater than ct, greater than equal to. And it's going to be equal to psi of minus 1 over c times x minus ct whenever y is, whenever x is less than or equal to ct, okay? And so even though the only arguments that I can plug into phi or psi are positive ones, by performing this transformation on the argument of f here, I ensure that the only thing that I'm passing in there is a positive argument. And we're going to see this again and again when we do method of characteristics on initial boundary value problems, when we do the wave equation as an initial boundary value problem, when we do the heat equation. There's always this issue of how the initial condition and the boundary condition fit together. And we only have data in that case that's relevant to when our arguments are positive. So whatever goes into, the argument of these functions that we have specified, we have to make sure that they're positive. So in this case, this is how we construct that for our transport equation. You'll see this idea sort of come back over and over again. So that's why I wanted to circulate back through it. So questions about this? Okay. All right. So we'll move on now to just a few words about Inviscid-Berger's equation, okay? This is one of the first nonlinear partial differential equations we'll see. I'm just gonna sort of flash through it really quick. We'll come back to it later. Inviscid-Berger's equation is derived from sort of more sophisticated descriptions of nonlinear wave dynamics. But in its simplest form, it just says that the partial derivative with respect to time of some unknown concentration plus that concentration multiplied by the spatial derivative is equal to 0. Okay, and what we can show is that this has an implicit solution, okay, given by u of xt is equal to u0 of x minus ut, okay, where u0 is our initial condition here. Okay, so looks a little peculiar because it's an implicit solution, but you can check and plug this in and see that it works, okay? And you'll have a chance to do this in some homework exercises, okay? But I want to demonstrate what's different about Berger's equation as opposed to the linear transport equation, okay? And I think I have, well, I don't want to try and go into that territory that may be covered up by video. So, so let me just exemplify the difference here. So if we look at the linear transport equation, okay, and we actually look at the solutions as they evolve in time, we have a function of x, okay, and we start off, let's say, where x is just defined on all of the reals. We have some initial concentration profile of u. It's just going to be translated in time, and it's not going to change shape at all, okay? So that's supposed to not have changed shape at all, okay? This is what happens with linear transport. In contrast, if we look at Inviscid-Berger's equation, u sub t plus u ux equals 0, and we start off with some initial concentration like this, u0 of x, then what happens is that because the speed of the substance, or could be a population or something like that, determines the speed of the wave at that point, this part up here is going to move faster than the part in front of it. And so what happens is you get an accumulation of substance at the front of this traveling wave. So as we move together in time, this is going to steepen. So there's a steepening here due to stuff at the back moving faster than stuff at the front. And what happens over time is that eventually you get what's called a shock, okay? You get buildup basically at the front of this wave, okay? And there's ways to handle this, but you can't use, sort of standard linear methods in order to understand this. And you also need some semblance of understanding of weak solutions, because you all of a sudden have generated a discontinuity. okay? So what happens now is that the implicit solution is invalid, okay? And you basically need a weak solution in order to address that, okay? So that's far off in the class, but I just wanted to show how even a kind of simple modification of the linear transport equation can massively change the types of solutions that you get, okay? So that's a sort of drawing a contrast between linearity and non-linearity, even